so we're just about there. We've wired up the circuit and just getting the last part in now. A bit difficult to get these larger components in. There we are. With the use of some pliers, put that large capacitor in the board. Right, well, today's lab, we did this as a demonstration earlier in the day, and I've taken the opportunity now to go ahead and actually do a video of this. The lab calls for a small circuit comprising a voltage divider made of two 4.7k resistors, a 0.56 microfarad non-polarized capacitor, and the dual channel crow, and a 9-volt power supply to power the voltage divider. The frequency that we're using is 500 Hz, and we need a cable from the signal generator that's connecting into the capacitor, and from the same point on that capacitor we need a signal going to channel 1 of the oscilloscope. All of the ground points are connected together to one common ground, which is also connected to the 0-volt rail from the power supply, which gives us 9 volts. The channel 2 on the oscilloscope is connected to the other side of the capacitor, which is at the junction of the two 4.7k resistors. On the oscilloscope, the rigol, we have a very smart function here, an automatic button. If we hit that button, the oscilloscope automatically adjusts to display two waveforms. This is the default. It puts one waveform at the bottom, channel 2, and channel 1 at the top. Already set to a scale that makes them easily visible and readable on the screen. Sometimes though, what we've got on the screen is not exactly what we need. So we need to go ahead and first of all get rid of the menu. We don't need that. I can take that off. And then I'll turn off channel 2 and I'll shift channel 1 down to the middle of the screen. Now it's interesting with digital oscilloscopes, commonly the middle of the screen is like almost a detent function in the positioning control. The waveform tends to stick in the middle just for a few milliseconds before it moves again while you're moving that control around. That's a very, very handy function as it makes the waveform symmetrical with the 0 line through the middle of the screen. Now I'm going to go ahead and make that waveform a little bit bigger, and then I'll turn on channel 2. Turn on channel 2. I'm going to move channel 2 waveform up to the same point on the screen. And if you look over here, we see the little tags that identify channel 1 and channel 2. And in fact, when the waveform is in that detent position along the 0 axis, these two tags, if you like, are lined up one directly above the other. There it is there. Now I'll make channel 2 a little bit bigger, and then another function on the oscilloscope that we've talked about is the horizontal section here, which is the time per division function on the oscilloscope. And as I stretch it out, you can see that there's a time difference between the two waveforms caused by the capacitor. We cannot easily get a reading from this. It's too small on the screen to get a decent reading of what that time shift is in milliseconds or microseconds, but if we're a little bit smarter about using the oscilloscope and we make the waveform a little bit bigger by using the scale control, that's for channel 2, and then I'll go back to channel 1. I'll do the same with channel 1, and then shift that along the screen a little bit. Use the trigger control to tidy it up and stop that like talk on the screen that I've got there. Sometimes triggering can be a problem on the oscilloscope. This is the circuit on the oscilloscope that controls the synchronization between the horizontal time per division and the vertical input. And it has a menu section on here and an adjustable trigger level. With the trigger level control, by moving that up and down the screen, you may be able to find a position where the triggering is smooth and stable. But if you can't, then simply hit the trigger menu button on the screen and possibly come down to the setup area down the bottom, and then possibly have a look at the coupling and see if you can change the filtering. At the moment it's set for simple DC coupling. If we change that for HF reject, high frequency reject, that should clean up the signal quite a lot, and then we can turn off that menu. The fact is that there's probably a lot of stray noise in the room, and also because I've really amplified the input signal to the vertical amplifiers in the oscilloscope. I've boosted the level of noise on the signal, and that's probably playing a bit of havoc with the time-based circuit, the triggering circuit. Anyway, that's nice and stable now, and we can go ahead and we can do a bit of a measurement. Now it's very important to make sure that the two waveforms are superimposed over each other, or that is, they're both sitting centralized on the 0 axis. We've increased the gain to really boost this vertical level and give me a nice, easy to read separation here. Now, using the horizontal control, I can move this waveform along the screen. I take note about what the horizontal is set to. It's currently set to 50 microseconds per division. And then I can read, and then I can read off the screen that I've got about 1.5 divisions. 1.5 divisions at 50 microseconds per division. 1.5 divisions at 50 microseconds per divisions equals 75 microseconds. And that is in fact what the time separation is between the two waveforms. And that time separation is caused in this circuit because of the capacitor coupling of the AC. Now it's time to go and have a look at the period of the waveform. So we'll go back to the oscilloscope, and the easiest way to put the oscilloscope just back to the beginning again is come up and press the auto button. Press the auto button, the oscilloscope rejigs and comes back with channel 2 on the bottom, channel 1 on the top. I'm only interested in looking at the period of the waveform, so I don't need channel 2 to be turned on. I can turn off channel 2 by pressing its selection button twice. I'll move channel 1 down the screen, and then I'll increase the level on channel 1, and then I'll go across to the horizontal section and I'll change the time per division setting. And then using the horizontal position control, I'll move that waveform along till I've got it at the beginning of the edge of the screen. Doesn't matter whether I've got the positive half cycle there or the negative half cycle there. The fact is I'm interested in one whole 360 degree cycle. We count the divisions: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions. 10 divisions on the screen. The time per division is 200 microseconds per division. Let's have a look at that. 10 divisions at 200 microseconds per division. So in fact, that works out to be 2000 microseconds for the period of the waveform. Or if you like, you could say 2 milliseconds. But let's be smart about the mathematics. In this case, I'm looking for the phase difference or the time difference between the two waveforms. So if I keep this in microseconds, and then knowing that I had 75 microseconds time difference between the two waveforms, I can use this equation. I can use the separation between the two waveforms, 75 microseconds, and I can put that over the top of the entire period for the waveform for 360 degrees, which was 2000 microseconds, and then I can multiply that by the number of degrees in one cycle. That's 360 degrees. And then if we do the calculation on that and we work it out, we come up with 75 microseconds divided by 2000 microseconds times 360 degrees. And that's what I said before. If you're a little bit smart about the maths, because if you make them both in microseconds, then you haven't got to worry about the exponent on the end. We can just cancel out the microseconds and work it in 75 divided by 2000 divided by the 360. And that's going to be equal to 13.5. And that is, of course, degrees, because we've taken a ratio there times the number of degrees. So 13.5 degrees of phase difference between the two waveforms. Let's do that again at a different frequency. That was again at 500 Hertz. Let's bring that down to 400, 300, 200. Let's bring that down to 100 Hertz. And of course we'll go back to auto function on the oscilloscope. And there we are, our two nice default positions for the waveforms. Again, what did we do? We want to put these both smack in the middle of the screen, as we can see by the edge marker here. Select channel 1, bring channel 1 down to the same point, and then we'll make each waveform a little bit bigger. Select channel 2, make him a little bit bigger, and then to the time per division, we'll expand the whole thing out. And this time we probably don't have to magnify the signals too much. It's quite clear to see that we've got a lot of time difference now between the two waveforms. So in fact we can see that we've got 1, 2, 3 divisions of time difference. We can see that we're on 500 microseconds per division. So we come over here, we look at that and we say we've got 3 divisions at 500 microseconds per division, and that's going to equal 1500 microseconds of time difference between the waveforms. Now what are we interested in? We need to find out what the period, so the period of the waveform. And of course we can do that by going 1 divided by the frequency. So in this case we had 100 Hertz, 1 divided by 100, and that's going to be equal to, we'll go to the calculator, we don't need to, but we'll do it just as a matter of fact, 1 divided by 100 equals, and that's going to be 10 milliseconds. 10 milliseconds. Now, that was the mathematical way of finding out what the period is. 1 divided by frequency, 1 on 100 Hertz, 10 milliseconds. However, we could have come back here, we'll go back to auto again. We'll get rid of channel 2. We don't need channel 2. Bring channel 1 down the wave, down the screen. Make him a little bit bigger. And we'll use the time per division control to stretch that out until I can get one complete cycle on the screen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions. 10 divisions at 1 millisecond. 10 divisions at 1 millisecond. Again, you can see 10 milliseconds is the period. Now, to find the phase difference between the two waveforms, we're going to have the 1500 microseconds divided by 10 milliseconds times 360 degrees, and that's going to be equal to, let's do that on the calculator, the 1500 exponent minus 6 divided by 10 exponent minus 3 times 360 equals 54. 54 what? 54 degrees of separation between the two waveforms. I've used Circuit Maker software to construct the circuit that we've worked with today, and this is with the 500 Hz showing the 560 nanofarad or 0.56 microfarad capacitor, and the effect of the two resistors in that voltage divider. Now the voltage divider was really used in week 1, where we looked at the DC isolation properties of a capacitor, and we saw that the DC from this voltage divider does not get back through the capacitor to damage the signal generator, but the AC from the signal generator can effectively pass through the capacitor, and then it can ride on top of the voltage which is sitting here, which half of 9 volts, of course, with two identical resistors is 4.5 volts. So if we had 2 volts peak to peak, which was asked for in the lab, that would be riding on top of that 4.5 volts. Today though, what we're interested in was merely looking at the phase shift across the capacitor, and we can work this out mathematically, and I'll go ahead and do that. But before we go too far with that, we need to understand something clearly. Ground, of course, is also, it's a DC ground, and it's a ground for AC, so no AC can be developed at this point. It's all going to be shunted to ground. So the AC is going to be developed across this resistor, but what about this resistor here? The AC is also going to be developed across this resistor, because the effective AC resistance, or we haven't studied the word yet, but we'll learn that the impedance of the power supply is a virtual earth for AC as well. So the equivalent circuit for this, I'm just going to do some modifications here. I'll get rid of that 9 volt rail. I'll duplicate that and bring that across to here, and then we'll bring that down to there, and that is in fact the equivalent AC circuit now for what we had today. So you can see now, I hope, that the two resistors are effectively in parallel. So half of 4.7k is 2.35k, and that is the AC load that the capacitor is looking into. So I'll jump from here across to the graph paper, and we'll run some AC analysis on that and see if we can duplicate mathematically that 13.5 degrees that we came up with in the lab. Alright, we've got a graph paper now to work with, but first of all we'll run some calculations on what we had. We know that the capacitor at 500 Hertz, the capacitor is going to have a capacitive reactance XC of 1 on 2 pi FC. and that's going to be equal to, if you go ahead and calculate that at 500 Hertz and using 560 nanofarads, it's going to work out to 569 ohms of capacitive reactance. And the other thing that we can go ahead and work out is the impedance. The impedance, if we use the polar function on the calculator, it's probably easier, and it'll just be pole of the resistance, the equivalent resistance, which I'll sort of put here REQ, and that'll be 2.35K, and then the reactive component would be 569 ohms, and that would give us a impedance then of, just looking at my notes, 2,417 ohms. So let's go ahead and plot those on the graph. We know that the resistance, so I'll work with this graph with XC down this axis, of course, and R along the horizontal axis. R was 2,350 ohms. There's 10 divisions here, so if we call them 200 ohms each, there's about 2,400, so about 2,350 about there. 569 ohms, we'll keep the same scale, so there's 200, 400, 600, 569 ohms there, so that would bring me out to about there. And then we just run a bit of a dotted line out there and a dotted line down there, and then we might even change the colour to this resultant. This resultant in this vector diagram is going to represent, of course, the impedance of 2,417 ohms Z. And when we ran the polar function, we also worked out that we got 13.6 degrees there of circuit phase angle, and the circuit phase angle represents the difference between the source voltage, the generator voltage, and the circuit current. And although I've plotted this graph against XC and R and Z, that could have easily been VC, VR and VS supply voltage there, and we get the same angle, of course, 13.6 degrees. So the mathematics gives us the same degrees of separation between the two waveforms because of the phase delay, the phase shift through the capacitor of that 13.6 degrees. In practice we worked out 13.5 degrees, I think it was, so on the day it wasn't too bad at all. So that pretty well wraps up what we've done with the crow today, or I shouldn't call it a crow, the oscilloscope today, and what we've done with calculating phase difference with a RC, resistive capacitive circuit.